last talk, so I'll make it quick so we can enjoy the sun. Um, I just thought it was funny talking about struct fields. I took a photo of truck wheels. But yeah, hi, my name is Matthew. I'm Friendly Matthew on GitHub. I love file formats, and like Adrian and Samuel and Jameson, I work at Pydantic. And at Pydantic, we built our own database using DataFusion that backs our observability platform. So what it looks like for users is you create this logfire span. You can dump whatever you want. You can dump your span messages in, and we visualize it for you in a very pretty way. So if any of you guys are interested in an observability platform that's not Datadog, maybe we can talk away from the security guards and outside this building. But anyway, what this logfire span does under the hood, it kind of compiles down to this crazy JSON payload. We add a bunch of stuff in there, like start timestamps, parent span ID. These are all things that we kind of abstract away for you. And notice, I guess, like importantly, this is the attributes section, and this is kind of where we are able to dump whatever we want. And we're going to zoom in here closer because per span, this JSON shape doesn't really vary, except this specific portion, right? Because there are keys that we can't predict ahead of time. All that to say is we have like this perfect schema that we can map out in our database, except this one column where we kind of feel this friction between our object and our actual relational scheme. So our existing solution is to store a JSON stringified version. So each row of data in the attributes field is just a stringified JSON, right? This isn't like the best, right? The read-write access patterns are kind of suboptimal. So suppose you have this query. It's a very simple query. We just want to see all the occurrences of this example span. And we also want to query by batch numbers less than 3, right? See the row count over there. I just realized this won't actually run, but that's besides the point. We can push down the first filter quite easily down to the Parquet opener, right? But we can't really push down the attributes filter because it's not really telling us much. What we have to do when we read it is we have to scan every single attributes row. We have to parse this JSON, and then we have to evaluate one key out of this gigantic JSON, right? And it's just not very optimal. And also, like, you know, when you write stringified JSON, it's not very space efficient. There's a new data type, and this is a quick corollary, but called variant. Snowflake, I think, had this pretty like markety article that said like it's a better way to represent your JSON workloads for OLAP databases. But I guess the quick high primer is that variant gives you this standardized shredding that kind of goes from this JSON object. It shreds it down per key into Parquet native columns. But how does these like Parquet like files, how are these actually like stored? And they're called struct fields, and that's what I'm going to be talking about today. So the goal at Pydantic is we want to use variant because we want better read and write performance. Variant data is stored as struct data in Parquet land, and we need to teach DataFusion how to read struct fields very efficiently. So what are struct columns? Well, a struct column is one column whose value is itself a nested object with nested fields. No, sorry, I read that wrong. It's a nested object with named fields. So you could imagine it's just JSON with a type schema, right? So it's represented in two different ways. In Erlang, it's represented as this top level field with the data type struct. But when you actually peel into like the layers of what's on disk, they're just 4 separate columns, each with their own natively typed benefits. So you could get like all the benefits of Parquet, but also, yeah, it's very easy to work with an arrow because we stitch it back together. Yeah, here's another look of how we store a struct field on disk. Notice how it kind of resembles this tree-like format. And the only thing here that I want to stress is that we only need to encode the leaf columns. The leaf columns is what we actually like have, like it's the meat and potatoes. This like schema of like how this tree is actually represented is stored as file metadata. So yeah, we're teaching the pushdown checker about struct fields. This is the example, and I'm gonna show how we can actually push the second filter down into the Parquet opener. Um, so the pushdown checker is a struct that walks through an expression tree, a physical expression tree, to collect information about which columns the Parquet opener can actually read. Right now, it's quite limited. It can only read primitive columns. So like these are like integers, float 64 columns, right? Nothing crazy. But now we also have to detect when this column that we're referencing is a struct field column, and also if it's in the file schema. Um, yeah. So this is what I did. Yeah, this is what I did. Everything else was written by much smarter people, but this is what I did. What we do here is we collect a bunch of different paths that access the struct field column as we're evaluating this tree, so that by the time we hand it off to the Parquet opener, it'll actually be able to understand in this struct field, which leaf columns do we need? And yeah, I guess like we just store the column indices, so it's pretty compact as well. Um, Now, do we need to like implement this mechanism all by ourselves? No, because DataFusion it loves dynamic dispatch if you read the code. It implements a tree node visitor, which is a trait that lets you analyze, that kind of walks you through a physical expression tree. Right, Andrew? Yes. Phew, okay. Yeah, and then this trait specifically, so it does different traversal methods, right? But F down is the pre-order traversal that does two things here, right? It collects every column and struct field paths that the predicate touches, but then it also shakes this tree and makes sure that there's nothing that's actually going to block us from pushing it down. And then these accumulated paths are eventually what we hand off to Parquet. Um, you don't need to read this. Just know that there's great numbers here. But this is just like a simple benchmark that tests the projection. Basically, what I do is I select star, or not select star. I select a specific leaf column from an attribute, and we can see that we get some huge wins. Yeah, that's really it. Thank you, guys. Does anybody have questions? Hi. It is available, yeah. Yeah. So that's a good question. It is available. It's got merged. It got merged. But there's still a lot to do, specifically with reading with variant. Like at our work, we write variant out in our data files and we use variant to actually like reference different things. But the reading is still like there's a lot of different things that we need to uncover. Like there's some parts with statistics that I kind of need to roll out. But yeah, eventually we'll get there. Yeah, again. Sorry? Yeah, so variant is a struct field. It just has this extension type called variant. But under the hood, like if you lift it over, it's just a struct field. So everything that you do for a struct field, you get all the wins for variant. With shredded variant, yes, but also yeah, who knows? But yes, yeah, I agree. Yes. All right, next question. Yeah.
That's for just reading any struct column, right? Not variant specific. So anyone who's
Yeah,
reading struct gets those struct fields, gets those speed ups.
exactly. Yes. All right. Well, make sure to yeah, thanks guys.
Just close it. All right, everyone. That's all the talks. So thank you everyone for coming. It's amazing to get so many smart people in a room. I don't know if there's any pizza left, but I think we have, some time to mingle and keep chatting and ask more questions now. But yeah, thank you everyone.